Hello, so we've seen how linearization works, the kind of general method behind linearization, but let's actually see an example in practice, okay? And the example we're going to use is the logistic model, okay? So if you remember, this is just the general form of the ODE, okay? We have a first order ODE, it's going to be the derivative on one side and just some function which involves, the thing which we're differentiating, which in this case is n, that's our function, okay, on the other. Okay, so remember what the logistic model was. It was the rate of change of our population was equal to, well, it was our growth rate times our population, but then we had to, that was kind of the exponential model, but then if you like, there was an extra little bit which is added on that kind of capped growth, and it was called carrying capacity, and we had to add this thing on in order to get the population to behave exactly how we would expect it to behave. And this is 1 minus n over k bit. Okay, so first things first, we need to find the equilibrium points of this thing. We need to find the equilibrium points of this thing. Before we go about linearization, we have to go about the equilibrium point. So what's the equilibrium point going to be? It's going to be when dm by dt equals 0. Okay, so that implies that basically this right-hand side, if you like, this f of n, I suppose, is equal to 0. Okay, so in other words, we end up with Rn times 1 minus n on k is equal to 0. Now, so basically this is trying to find the equilibrium point. Now, we know that this r means growth rate. Okay. Now, growth rate is either positive or negative. Okay. Very rarely is it just constant. In other words, there's no growth effectively. The population either grows or it decays. It's near on impossible for a population just to remain constant. Okay, it always changes, because if nothing else, people are always going to die. All right, even if you say nobody's allowed to give birth, or nobody's allowed to have children, people are going to still die. So therefore, this r cannot be equal to 0. Okay, so therefore, what we're left with n can be equal to 0, or k can be equal to 0. Okay, so let's have a look. So then effectively, if we know this is not equal to 0, we can just remove it from the system, okay, because we're not interested in it. We're not interested in it because we know it's not going to equal to 0. So therefore, what we're left with something times something. This n can be equal to 0, or, so we've got two things multiplied together effectively, and, it's equal to 0, so therefore one of them has to be equal to 0. Okay, so either n can be equal to 0, or this 1 minus n on k can be equal to 0. That's why I removed the r, because, otherwise we'd have Rn can be equal to 0. So then we'd have three things that can be equal to 0, but r can't be equal to 0. So let's just remove it. Okay. So in other words, we can have n equals 0, okay, or 1 minus n on k is equal to 0. Okay, so that's our first equilibrium point, actually. N is equal to 0, so our population is 0. So that's the first equilibrium point. Okay, what's the other one? What's the other equilibrium point? Well, hopefully you can see that just by, before I could try and expand this out in a minute, and I will try and expand it out in a minute just to verify it, but the next equilibrium point should be when our population is at its carrying capacity. Because remember what an equilibrium point means. It means no state of change. Well, if there's no population there, then obviously there's no state of change. Then fairly obviously that should be, an equilibrium point. So that's the case when n equals 0. But the next one should be when the population is at its carrying capacity, because the population can't grow any further. Population physically can't grow any further when it's at its carrying capacity. Remember that population can't really reach its carrying capacity, but suppose theoretically it can. When it's at its carrying capacity, a population can't grow anymore. There's physically not enough resources to allow the population to grow. So therefore, we would expect that the next one should be at n equals k. And in fact, if we expand this thing out, that's exactly what we get. So we get 1 equals n on k. I'll just take the n on k on the other side. So therefore, when we multiply through by k, we get n equals k, okay, as expected. Get n equals k as expected. Okay, so those are our two equilibrium points, that one and that one, okay? And that kind of makes sense, okay? So, now we need to come on to the linearization. So we found the equilibrium points, now we want to come on to the linearization. So if you remember with our linearization, before we had dy tilde by dt equals f dash of ye times y tilde, okay? So now what we've got is our function. What was our function? A function f of n. Well, our function f of n, this is just Rn times 1 minus n on k. So f of n is equal to Rn times 1 minus n on k. Okay, so in other words, what we're trying to do is we're trying to place y, y is equal to n, okay, ye is our equilibrium points, so our equilibrium points ne. I suppose I could denote these equilibrium points with little ne's, okay, keep the notation constant, need to keep the notation the same, okay, and so therefore we also have y tilde must be equal to n tilde as well, okay, just by the same notation as we have before. So this is effectively our new notation, okay, if you think about that, it kind of makes sense, all right. So our function is Rn times 1 minus n on k. So that is literally, our function is our rate of change of our function. Okay, our rate of change of our population, and so therefore our rate of change of population is given by this thing. Okay, so that's our function. So if you remember, if you look in here, I can just make dn tilde by dt, yeah, because I'm just making a substitution now using these variables, is equal to f dash of ne, okay, times y tilde, which was n tilde. Yep. Okay, so this is now effectively what I'm trying to do. This is my linearization for this particular model. Okay, so therefore that means that I need to find the derivative of my function and then plug in my equilibrium values. Right, plug in my equilibrium values. So in other words, I need to find the derivative of this thing. Find the derivative of this thing here. Okay, so what is the derivative of this thing? Well, my derivative of this thing is, it's going to be, so I'm differentiating with respect to time. Well, what's the only thing that's dependent on time? It's going to be, 1 minute. Yeah, okay. This may not be the best way to tackle this, actually, because it's kind of difficult to see. You could use the product rule, I suppose, but what I'm going to do is I'm just going to actually consider this properly. So what I'm going to actually do is just expand this right-hand side. So we'll end up with Rn minus Rn squared upon k. Okay, so I'm just going to combine that into one constant like that. There we go. So, okay, then I want to find the derivative of this thing. So the derivative of this thing will be equal to, well, this is going to be r, because I'm differentiating with respect to n. So, this is just r, okay, minus, this is just a constant, the r on k, so I'm just going to keep it there. And then this is going to become minus 2n, okay, reduce the power by 1. So this is effectively what I end up with. And then if I just take an r out again, so r times 1 minus 2 on k, 2 on k times n. Okay, so this is effectively what I end up with. Okay, or even if I just write it like this, 2 Rn on k. So it looks a bit familiar to what we had before. So this is effectively what we need. And then we need to just plug my equilibrium points in here. Well, what are my equilibrium points? Well, I've got ne equals 0 and ne equals k. So these are my equilibrium points that I need to plug into this thing. Okay, so what is f dash of ne equals 0? Okay, that is going to be r times 1 minus 2 times 0 on k. Yeah, so that's going to go to 0, so it's going to be 1 minus 0, so it's going to be r times 1, okay, which is going to be r. Okay, so f dash of ne equals 0 is just going to be r. Let's have a look at what happens when we plug in ne equals k into this thing. So I'm going to end up with r times 1 minus 2 k on k. Okay, well, k on k is just going to become 1, right? So it's just going to become 1 minus 2. Okay, well, 1 minus 2 is going to become minus 1, yeah? So it's going to be r times minus 1, so it's just going to become minus r. Okay, so these are my two equilibrium points now. So this is my function evaluated at both my equilibrium points. Okay, so therefore, when ne equals 0, when my equilibrium point is 0, my linearization, remember what my linearization is, it's dn tilde by dt equals f dash of my equilibrium points. Now my equilibrium point is 0 times n tilde. Well, I've just found my equilibrium point at 0 is r. So effectively this is just r now. Okay, so it's just r. Okay. And then when ne equals k, so my equilibrium point is at k, I end up with dn tilde by dt equals my derivative of my function evaluated at my equilibrium point at k times n tilde. Well, what's my equilibrium point? What's my derivative of my function evaluated at k? It's minus r. Okay, so this is just minus r now. Minus r. Okay, and so those are just my two equilibrium points. Those are my two equilibrium points. Now, let's consider what we had before. So we had that, when we had the derivative, this is basically the end of the last video. We had that when the derivative was greater than 0, okay, that led to, what does it lead to? It led to the fact that ye, so whatever's inside the bracket, so our equilibrium point was unstable, all right, unstable. And then when it was less than 0, it led that ye, so our equilibrium point, was stable, or asymptotically stable, I should say. Asymptotically stable, all right. So what have we got here? Well, let's look here. So now my function is, in this case, so when ne equals 0, if I just replace this with ne now, this ye with ne, so my equilibrium point, it's no longer y, it's now n, okay. So my equilibrium point, my derivative of my function at my equilibrium point, so when n equals 0, my function is r. So if we just consider r to be some positive value, because fairly obviously it will be some positive value, okay, then I end up with a positive value. So therefore, when ne equals 0, okay, I get this case, it's unstable. Okay, I end up with unstable. Yeah, my equilibrium point is unstable. Okay, now let's consider the case when ne equals k. Well, when ne equals k, I get minus r. So in other words, that's negative. That's negative, right? So therefore, when it's negative, then I get that it's asymptotically stable. So that's asymptotically stable. Okay, so I get it's asymptotically stable. So here I have the stability of my points just using a linearization, just of the logistic growth model. Really nice, really straightforward. I didn't have to solve any ODEs. I just performed a nice, simple linearization, a little bit of differentiation. I was instantly at the end of it. Probably, okay, I talked it through it, but I could probably do it in a few minutes. And I was instantly able to just determine, the stability of the equilibrium points.